Hello, Mr. Collier here. Today we're going to continue our discussion of atoms by talking about how to count and measure the size of atoms. We're going to talk about the mole. Before we get to the mole, we need to talk about how we measure individual atoms, and that's with a unit called the atomic mass unit, the AMU. So we measure things like height in feet and inches. We need to have some sort of standard for reference. What is a foot? What is an inch? And in this case, what is an AMU? Scientists picked the carbon atom as the reference for the atomic mass unit. Specifically, we picked the carbon-12 isotope, and we decided that 1 AMU would be 1/12 the mass of a carbon-12 atom. So carbon-12 is 12 AMUs. Since carbon-12 is 6 protons and 6 neutrons, and they're about the same size, a proton and a neutron each weigh 1 atomic mass unit. Now, if you get into the nitty-gritty of chemistry, you'll find that they're not truly 1 AMU each, but for what we're doing, it's close enough. Now, there's a problem with atomic mass units. They're a little bit impractical. So if you take your pencil and put a single dot on your paper, you've put trillions and trillions of carbon atoms onto your paper. Atomic mass units are just so small. Atoms are just so small that it's really unrealistic to talk about any real-world samples of elements in terms of AMUs. So the solution to this is to, instead of talking about AMUs, to talk about the mole. So, very clever, what scientists did is they said, so if carbon-12 is 12 AMUs, 1 mole will be 12 grams. This will make the conversions very simple. So let's get into some more detail on this. The word mole represents a very large number. That number is 6.02 times 10 to the 23rd. We also call it Avogadros number. Think of this word like you would the word dozen. A dozen donuts is 12 donuts, a dozen eggs is 12 eggs, a dozen of anything is 12 of that thing. A mole is exactly the same. A mole of an element is 6.02 times 10 to the 23rd atoms. A mole of anything is 6.02 times 10 to the 23rd of that thing. So how big is this number? So I'm going to give you a couple examples to explore its immense size. So if you had a mole of pennies, 6.02 times 10 to the 23rd pennies, there's 7.5 billion people on Earth, give or take. So everyone would get, right, if you take that and divide it out, everyone would get 8.02 times 10 to the 11th pennies. Well, what is that? That is $8 billion per person on the entire planet if we distributed a mole of pennies. It's a staggeringly large number. Let's do some more silly examples. A mole of marshmallows would cover the United States 105,000 kilometers deep. A mole of watermelon seeds would fit inside of a watermelon slightly larger than the moon. A mole of donut holes would cover the entire Earth 5 miles deep, and a mole of pennies would make at least 7 stacks that would each reach to the moon. It is a huge, mind-blowing number. So a mole is going to be a number, it's huge, but it allows us to talk about atoms in a more practical sense. It's the number of atoms in exactly 12 grams of carbon-12. We call it Avogadros number, as I mentioned. It's 6.02 times 10 to the 23rd. The nice thing is that we can talk about atomic mass of an individual atom in atomic mass units. And we can talk about molar mass as the mass of 1 mole of a substance in grams. And they're going to be the same number. So the mass of an atom of carbon-12 would be 12 AMUs, and the mass of a mole of carbon-12 would be 12 grams. For zinc, it's 65.4 AMUs for an atom and 65.4 grams for a mole of it. So here's just a few more examples using the periodic table. We've got some elements, and each of them have an atomic mass and a molar mass that are the same numbers with different units. Next, I want to talk about using moles to do conversions. So the number of grams comes from the periodic table. We call that molar mass. The number of atoms is always 6.02 times 10 to the 23rd, and the number 1 always goes with the term moles. So let's take a look at some examples to make sense of this. 1 mole of carbon is equal to 6.02 times 10 to the 23rd atoms of carbon, which is equal to 12 grams of carbon. What about other elements? 1 mole of silver is 6.02 times 10 to the 23rd atoms, because that's the definition of a mole. But for silver, it's 107.9 grams for that same number of atoms, because each atom of silver is heavier than each atom of carbon. Or for arsenic, you've got 6.02 times 10 to the 23rd atoms for a mole, which is 74.9 grams. These gram numbers come from the periodic table. So let's do some conversions. Say I have 15 moles of iron. How many atoms of iron is that? So I start by writing down what I know. Next, I want to create a conversion factor that allows me to cancel out the units I want to get rid of, in this case it's moles of iron, and lets me convert to the atoms I want to end up with, which in this case is atoms of iron. So my conversion factor puts moles of iron on the bottom, which allows it to cancel. And then I put atoms of iron on the top. And the number that goes with atoms is always 6.02 times 10 to the 23rd when I'm talking about moles. I simply simplify it, and I get my number of atoms of iron. Let's do another one. Say we wanted to go from a certain number of atoms of magnesium to moles, kind of just the opposite of what we did in the previous one. We're going to start with a conversion factor, and again, our goal is always to put the units we want to get rid of on the bottom. The number 6.02 times 10 to the 23rd always goes with atoms, and the number 1 always goes with moles, and that'll go on the top in this case. Our units cancel, and we simplify, and get our answer. We can also go from grams of a substance to moles. For this, you're going to need to reference the periodic table. So now I'm going to look up bismuth on the periodic table and find its molar mass. That is the number with the decimal that's on the periodic table. For bismuth, it's 209.0 grams per 1 mole. Grams goes on the bottom so that it cancels, and 1 mole goes on the top. I solve, and I find how many moles. Also, please note as you do these conversions, you're going to keep the same number of significant digits you started with. So here we had 4, which is why I've reported my answer to 4 significant digits after the conversion. Here we can go from atoms to grams, again, using the same pattern. We're going to write what we know, pick a conversion factor that gets rid of the units we want to get rid of, in this case atoms, and 6.02 times 10 to the 23rd always goes with atoms. Those cancel. We put grams on the top, which is what we want to end up with. I got that number from the periodic table, and then we simplify. And that's it for converting from grams to moles to atoms. Try it, and I think it'll start to make some sense.